In this video, we're going to cover section 6.3. We're going to be talking about vectors in a plane. This is day one of 2 days for pre-calculus honors. And then here are the important concepts that you want to make sure you understand at the end of this lesson, because there is a lot of vocabulary in this lesson. If you don't know what the words are asking you for, even though the mathematics involved is really sometimes not more than addition and multiplication, maybe taking some square roots. If you don't understand the vocabulary, you can't answer the questions. So we're going to be talking about component form of a vector, magnitude of a vector, and some of this you may know if you've taken physics or are taking physics right now. We're going to talk about vector operations, so like adding or subtracting vectors. We're going to talk about a unit vector. So this is a big one where the concept really is very straightforward, but sometimes students will forget, what they're really asking for when they talk about a unit vector. And then we'll talk about linear combination of vectors. So these are the main concepts from this part of the unit. So let's talk about a scalar. So a scalar has a magnitude but not a direction. So we think of a real number as a scalar even if they are negative. For example, a speed of 60 miles per hour is a scalar. So it tells us how fast we're going, but it doesn't tell us what direction we're going. Now, a vector, on the other hand, has both a magnitude and a direction. Okay, a vector v has a magnitude. This is our notation for magnitude. We use these double absolute value signs. This is just the length of the vector. For example, the directed line segment, this arrow down here below, is a velocity vector. So now, again, we know we're going 68 miles per hour, and we're kind of going up and to the right, or if we think about it in directions, we're kind of going northeast direction. So equivalent vectors are vectors with the same magnitude and direction, but not necessarily the same position. So all of these vectors here, they have the same length. Okay, and we can calculate the length of this just using the Pythagorean theorem. If we set up a right triangle here, this would be 6 and this would be 5. So the magnitude of this vector v, we'll call that v, so the magnitude, and we'll get to this in the video again, we'll just give you a little preview here, it would be the square root of 6 squared plus 5 squared, so that's 36 plus 25, or the square root of 61. So each of these is going in the same direction. Okay, we could also talk about the direction in terms of slope. So each of them has a slope of 5/6, and it has a magnitude of square root of 61. We would call them, again, equivalent vectors. Now this one here, this is going to be how we show our vectors most of the time. We notice it has its vertex at the origin, or its endpoint at the origin, and that's what we're going to call, scroll back up here a second, component form of a vector. All right, again, just a little preview. We're going to get to that in a moment. So let's look at a quick example. We're going to let u be represented by the directed line segment from P, which is at 0, 0, to Q, which is at 3, 1, and let V be represented by the directed line segment from R at 2, 2 to S, which is at 5, 3. So sketch the two vectors and decide if U is equal to V. Now, when I write these vectors, I'm going to write them with that little half arrow on the top. But when they're typed, sometimes they'll just be written in bold. All right, so let's go ahead and graph these. So we have P at 0, 0. And we have Q at 3, 1. So here is our directed line segment from P to Q. And then I have R at 2, 2. So here's R, and we have S at 5, 3. So here's S, and here's our other directed line segment. So they kind of look like they might be equivalent. So let's look at the magnitude of PQ. So one side of this right triangle would be 3 and the other would be 1. So that's just going to be the square root of 3 squared plus 1 squared. So that's the square root of 10. And let's also, so that's the magnitude. Let's take a look at the slope of it. The slope of PQ. So the rise would be 1. So that's 1 over 3. All right, so that's for PQ. Now let's take a look at RS. So the magnitude of RS. So again, if we look at a little triangle here, we're going from 2 over to 5, so that's 3 units, so that's 3 squared. And we're going from 1, or from 2 up to 3, so that's 1 unit. So that's square root of 10, so the magnitude is the same. And let's again check the slope of RS. All right, so slope again is going to be 1 over 3. So these are in fact equivalent vectors since they have the same magnitude and direction. All right, and then again, slope is just one way to denote the direction. All right, so we talked about this just a second ago, but component form of a vector whose initial point is at the origin. All right, and we will almost exclusively deal with vectors in component form. And when we use these angle brackets here, that's how we know that it's in component form. Okay, if it's not in component form, it won't have these angle brackets here. So basically, we're looking for an equivalent vector that has an endpoint at the origin. And that simplifies a lot of our calculations. So sometimes what we'll have to do is we'll have to put a vector into component form. So the component form of a vector, if the initial point is P, whose coordinates are P1, P2, and terminal point is Q with coordinates Q1 and Q2, then the component form PQ, so we're going to do the terminal minus the initial for the x coordinates and the terminal minus the initial for the y coordinates, and that will give us the component form. So let's make a little note here. This is the terminal point. This is where the arrowhead is. So basically what we're doing is we're taking a vector which might be somewhere in the coordinate plane, and we're going to move it so that it ends up at the origin. We're just going to slide it over there, move it over to the origin. All right, and again, when you see these angle brackets here, you know that it starts at the origin. All right, here's another concept, unit vector. Unit vector is a vector with magnitude equal to 1. All right, so if I have a vector and its length is 1, so here's a vector, this is 1, this is just a pretty simple one, and this is 1, well, this would be square root of 2, so this would not be a unit vector. But what we want to do is we want to find, so my coordinates here for this component form would be 1, 1, but what we want to find is we want to find the point along this vector where the length would be 1. Okay, so we want to find some point where this would be 1. So that's basically the idea of a unit vector. Okay, and this is the formula. So we're going to take the components, the x and y components of the original vector and divide the x by the magnitude and divide the y by the magnitude, and that will give us the coordinates of that little point right there where it would make the magnitude of that 1. So let's look at an example. The component form and magnitude of the vector v has an initial point of -2, 3 and terminal point -7, 9. So we're going to find the component form, we're going to find the magnitude, and also for a little extra bonus on this, we're going to find the unit vector. So we'll just call the initial point P and the terminal point Q. So PQ, we're going to do terminal minus initial, so -7 minus -2, comma, terminal 9 minus initial 3. So that's going to give us -5, 6. Okay, so basically we had a vector. I'm just going to do a quick sketch, -2, 3 and -7, 9. So it went like this, and then we just moved it so that it started at the origin. So now this point, which used to be at -7, 9, now is going to be at -5, 6. All right, let's find the magnitude. So we could find the magnitude using this formula up here, but since we already have it in component form, we just need to basically do the Pythagorean theorem like we did towards the beginning. So that's going to be -5 squared plus 6 squared. So that's the square root of 25 plus 36, or the square root of 61 again. All right, now we've moved this vector, so -5, 6 is maybe going to be somewhere around here. This is where the new vector is. We just slid it over so this point was at the origin. So what we want to do now is we want to find the unit vector. We'll call it u. So again, we're going to find the point along here somewhere that makes that little vector going in the same direction as the red vector, only 1 unit in length. So I have the component form, I have the magnitude, so all I need to do, based on this formula here, is take the component form divided by the magnitude. So the component form is -5, 6, and I'm going to divide it by the square root of 61. And then we'll just simplify this, so we're going to have -5 over square root of 61, comma, 6 over square root of 61. And we can simplify this to -5 square root of 61 over 61, comma, 6 square root of 61 over 61. So if we figured out what these decimal value was, the decimal value of the x and y components, then we could graph this on here somewhere. So this would be the coordinates of this little vector in here, and then the magnitude would equal 1. That's the unit vector. So the directions a lot of times will ask for the unit vector in the direction of an original vector. All right, so I'm going to end this here. As always, if you have questions, make sure that you're pausing the video and writing those questions down and get those answered the next time you see me in class. And we'll see you in the next video.